Hello, everyone. I'd like to say thank you to the organizers for the opportunity to speak. It's a tremendous honor to be here. But I'm here for a job, right? In more ways than one. But I have to convince you of this theorem, right? I have to tell you about vanishing rank gradient via cost and this ideal Poisson Voronoi tessellation. So let's get into it. Let's remind ourselves of what the theorem was. We heard about it a bit on Friday. So for context, for all the cool cats out there in YouTube land, we just had a 3-day weekend. Yesterday was Bastille Day. It's like 9 a.m. So I think we could all do with a reminder of what this mini course is about. So the setting here is that I'm going to consider G some locally compact group. And you know, it's no secret, I have eyes for one group only. I want you to think SL3R. OK, and I want to introduce a bit of notation. So I'm going to be considering lattices inside of this group. You guys like lattices, right? Yeah, OK. Thought I was in the wrong place. OK. And the invariant that I'm interested in is a very group theory 101 invariant. It's called the rank. I denote it D of gamma. This is the minimum size of a generating set. OK. I call this the rank. It's unfortunate terminology because it conflicts with these other geometric notions of rank that we're interested in. It's a very basic invariant. You can think of it as a kind of complexity for the group. One thing I just want to point out, if you haven't thought about rank since you learned about it in your first group theory course, is the rank is very hard. Okay, this is a homotopy invariant. That makes it a lot harder to compute than homology invariants. And I can illustrate this by thinking about like finitely presented groups. Right? If you're looking at finitely presented groups, there is no magical algorithm that takes some finitely presented group and tells you if the rank is 0 or not. Right? Rank being 0 means the group is trivial. We live in a cruel world, but we're still interested in the rank. And we're restricting the class of groups we're looking at. We're not looking at all finitely presented groups. We're looking at lattices, and lattices are very nice. So yeah, I just wanted to emphasize that rank is hard. It's a slippery invariant. So yeah, let me remind you of the main theorem for this mini course. OK, so this is in the paper with Mikolaj. And so the setting here is that I'm going to look at a higher rank group. OK, so our friend SL3R is the candidate. It's also some other groups, but the Lie setting is the most interesting. And then I'm going to take what's called a Faber sequence of lattices in this group. And I'm going to restrict to the case of co-compact lattices. OK, I'll say something about this assumption of Faberness. It's some kind of non-degeneracy assumption. So what does the theorem state? It states that the rank gradient vanishes. So hopefully I have enough room here. That the limit as n tends to infinity of what I'll refer to as the normalized rank. So this is the rank of the lattice. Sorry, it gets a bit small. Minus 1 divided by the covolume. This is 0. OK? So this is uniform vanishing of rank gradient. OK, so this is the main theorem. This is supposed to be the hook that we use to lure you in. Because really what we're going to talk about is something called cost and Poisson point process. But I should tell you some further context for this theorem. So first of all, I mean, why are we looking at these expressions? Why, in particular, do we divide by the covolume and not covolume squared or log covolume or something like this? This goes back to work of Jagiellonian. So Jagiellonian had a beautiful PhD thesis, and he studied how rank behaves versus the covolume, in particular for irreducible lattices. And he showed that quantities like this are bounded. In other words, the worst case scenario, you need some multiple of the covolume many generators to generate your lattice. Right. And so later on, this was conjectured that this uniform vanishing of rank gradient would be true for sequences of lattices. This is in a paper of Mikolaj Fraczyk, Jagiellonian, and Nikolaj Nikolov. In their paper, they refer to it as a provocative conjecture. So I'm hoping this means that the solution is also provocative. Right. Yeah, so what Jagiellonian did is kind of a Lie theoretic analog of what you can squeeze out of the Nielsen-Schreier index formula. The Nielsen-Schreier index formula tells you exactly how rank behaves for finite index subgroups of free groups. And he proved a Lie theoretic analog of that. So more comments on these assumptions. What's the deal with this Faber sequence business? I'll speak about it more on Thursday, but all you need to know is that it means that the corresponding sequence of quotients forms what's called a Sophic approximation for the group. Okay? This assumption will play a somewhat minor role. You'll see that it's actually just a one-line computation that I need it for. The other thing to note is that this Faber condition is essentially automatic. Okay, so as long as you don't pick your lattices in a very stupid way, like picking the same guy over and over again, it will be Faber. This is a consequence of the famous Seven Samurai paper. We call it the Seven Samurai paper for two reasons. One is that Mikolaj is somewhat of a cinephile, and he loves the films of Kurosawa. And the other reason is that it's way too hard to remember 6 of your co-authors' names. OK, so that's the main theorem. That's supposed to be the hook. And now I'm going to tell you 2 more theorems. I'll get them up on the board very quickly. And this main theorem will follow from them essentially immediately. So I'll follow Roman's lead and use this convention. So theorem A. So this is joint work that I did with Mikolaj Fraczyk. He's a Hungarian fella, so you got to pronounce the T. That's the only trick. And then independently, around the same time, Alessandro Carderi proved a theorem which, yeah, I'll talk about this history on Thursday. I mean, there are important technical distinctions between these 2 theorems, but in a philosophical and a sort of functional sense, they're equivalent. His proof is also quite different. He uses ultrapowers, and we use weak convergence. But the point of the theorem is the same. So the setting here is that we take G to be compactly generated. Okay, so it's quite a general theorem. And again, I'll take a Faber sequence of co-compact lattices. This is something else that I was supposed to say about this theorem. So it is true for non-uniform lattices, but you have to work harder. And we're trying to give you the minimum viable product. So we'll focus on co-compact. And the other thing to know is that there's a fellow, Raz Slutsky. Raz has a fantastic paper with Alex Lubotsky where they essentially optimally control rank for non-uniform lattices. So this is the other reason to focus on the co-compact case, because why do all this extra work if some guy already beat you? OK, so what is the theorem? The theorem states that if I look at the normalized rank again, and now I'm taking it worst case scenario, so I look at the lim sup. So the rank of the lattice minus 1 divided by the covolume. There's a reason why I include this minus 1 here. You'll see it very soon. This turns out to be dominated by, or controlled by, some mysterious quantity for you for now. Something called the cost of the Poisson point process on G minus 1. OK? And I won't leave you in suspense. I'll talk more about this theorem, but I want to get the other one immediately on the board. So this is theorem B, and this is what we actually prove in the paper with Mikolaj, is that if G has higher rank, then the cost of the Poisson point process on G, Poisson point process on G, is equal to 1. OK? And so just a bit of jargon. You can take this as a definition for now. Saying that the cost of the Poisson point process on G is 1, this is equivalent to saying that the group has what's called fixed price 1. So during these lectures, I will explain what this terminology is. Yeah, I'll talk more about these theorems, but let's just have a gander. OK, it seems to me that if I take theorem A and theorem B, you guys are all familiar with the rules of logical inference. If we take the conjunction of these two statements, oh, I reckon that gives us the main theorem, right? Wonderful. OK, so job done. You're all convinced? Off to the pub? Is the gramophone open or no? Questions?
When you say higher rank, does it include probability?
No, but you could probably make it work if you're sufficiently motivated. OK, yeah, it's not that easy, right? We're going to have to do a lot more work. But I mean, you see that the logical structure is quite clear here, right? These two theorems, they piece together, and they give this. And at this point, you might be wondering if you ever, cracked open this paper with Mikolaj. I mean, what's the big deal? We prove something about rank, but you open up the paper, and we don't say anything about rank. All we talk about is cost. And this isn't really a bait and switch. So let me give you a quick spoiler for this mini course. It will follow from the definitions that, well, I mean, this cost, it's some numerical invariant that you associate to PMP actions. I don't know so many PMP actions. This lattice shift one, that one looks good. And what I'm telling you is that its cost minus 1 is equal to the rank of the corresponding lattice minus 1 divided by the covolume. OK? So yeah, this is not a difficult statement to prove once you have processed the definitions. It's related to this suspension construction or induction construction that Homin spoke about in his course. But now maybe where we're going with this starts to make sense. If you're interested in studying things like this, limits of normalized rank, well, I'm telling you that they're the same thing as, well, limits of costs. So maybe it behooves you to start investigating how cost behaves with respect to limits. And that's what we're actually going to do. Okay? What else do I want to say about these theorems? No, I think that's just about it. All I have to do now is explain what cost is, right? OK, so yeah, the goal for this lecture is just to give you the big picture overview of what's going on here. So yeah, let's get into it. So what is? OK, what is cost? So some of you might recognize this formatting from the notices of the AMS. They have this series of articles, What Is? And the father of cost, Gaboriau, he wrote one of these. Okay, so if you're seeing cost for the first time, I highly recommend that you check this article out. It's fantastically written, and it's also quite short. It's just 2 pages. And it will explain what cost is. But I'll also explain cost with a slightly different perspective. So yeah, it's called Damien, the father of cost. Formerly, it was introduced by his advisor, Levitt. But it's really Damien who developed this theory and found all sorts of applications in ergodic theory, probability theory, operator algebras. Like, it's truly a fundamental invariant. And the perspective that they would probably tell you about what cost is the following. So it's the measured dynamical analog of rank. Okay, and that's the perspective that you would see if you take a gander at this what is article. The other place that you could look at, that I would recommend you check out if you're hearing about cost for the first time, is Damien's original paper. Okay, so it's a, yeah, I mean, I will warn you that it's a Invenciones paper, and it's 60 pages long, and it's in French, but it's very understandable French, and I mean, he lays things out very clearly. I mean, if you want to know about cost and you don't read this article, like you're quite the fool. So, yeah, the perspective they take is this one. It's the measured dynamical analog of rank, and that's what some in the audience refer to as classical cost. I hope, please don't use this expression. I'm too young to be old. I guess I'm part of the newer generation where I think of it in slightly different terms, and that's what I'm going to explain to you now.
Yeah. Is your rank like D of gamma or like rank of G?
Here? The like that rank, classical rank, if you will. Yeah. Okay. I mean, it strictly generalizes rank, and this is what we will see tomorrow. So yeah, don't be afraid to interact or whatever. That's something by it. So the way that I think about it is the following, or a probabilistic. Oh, that was supposed to be a small p. A probabilistic optimization problem. Okay, and that's what I'm going to explain to you now. So the setting here is I'm looking at my group. My group should be locally compact or something. And so my group is this, this shape. As a student of Mikolaj, I'm obliged to call these things potatoes. So I'll do that once and only once. And what I'm interested in is the following probabilistic optimization problem. I want you to take pi to be a random subset of this group. And you will not be surprised to learn that pi is the Poisson point process. So we heard a bit about this on Friday, and if you attend the exercise sessions, you'll learn what this thing is. I want to reassure you that this is an extremely explicit object, basically as explicit as it gets in probability theory. This is not something like, oh, the implicit solution to some 27-dimensional stochastic differential equation or something like this. I mean, it's a very concrete object. But I'll give you an alternative. Anyway, it's some kind of scattering of points that's kind of totally random inside of the space in a way that can be made precise. Maybe you don't know the Poisson yet, so I give you an alternative. The alternative is that you take a lattice inside of your group. You guys like lattices, right? Okay. So this is your lattice, your favorite lattice. And I like lattices a bit, but I like flicking coins more. And so I want to percolate this. Okay, so all this means is that you take this lattice, and then you independently flick coins for each one of its points, and you kill all the guys that get the tails. Okay, tails not so lucky. So I delete elements according to random coin flips. Okay, that gives you some random subset of the space. It's not really the Poisson, but it's like close enough for government work. So what is the actual optimization problem? This is an instance of the optimization problem. So now what I want you to do is to put an abstract connected graph structure, graph G on pi, subject to some natural constraints, but you want to minimize the number of edges. Okay, this will seem a bit vague at the moment, but I'll make it more precise. Okay, so the graph, it has to satisfy some properties. So it's G equals G of pi. It's a random graph. It should be measurable, measurably defined, equivariant, and this is the big one, and deterministic. Given pi. Okay, I'll explain more about what this means. And what you want to do is you want to minimize, in other words, in an infemal sense, minimizing 1/2 of what I'll call the average degree of G. Okay? So this is the cost optimization problem. I'm going to spend some time explaining, more about these conditions. But yeah, I give you this set of points, and you're supposed to put some graph structure on it, whatever it happens to look like. And you want to minimize this average degree, or 1/2 the average degree. And the way you get at the average degree, I'll explain this more tomorrow, but roughly speaking, you look in some finite window, W, and then you see finitely many points. You see just a little portion of a graph, and you take the average degree of that. And that's a random variable.
Okay. Sorry, maybe you mentioned this, but when you say equivariant, you mean equivariant with respect
to the natural shift action. If I shift the set of point processes and put the graph structure on the result, that's the same as if I put the graph structure on it and then shifted it. G equivariant.
And so where's gamma?
Gamma is just this random subset that you constructed.
The gamma was just an example, right?
Yeah.
So this is
Yeah. Yeah, so this is the problem. I will make it more precise tomorrow, but I'm just trying to give you the big picture overview and some of the salient features of this problem. So we're supposed to be looking at all these measurable, equivariant, and deterministic ways of putting a graph structure on this. It's not really clear these things even exist, right? I mean, maybe the first thing you would do is you just connect every point to every other point. That works, but it's, that one's woefully inefficient. Edges are expensive these days. So I'm trying to minimize the number of edges, minimize this 1/2 of average degree. But, it satisfies the other conditions. Why do we put these other conditions here? Measurability, equivariance, this strange one about determinism. I mean, what I'll point out is that if you drop either one of these conditions, this problem is trivial. Okay, this is something you'll see in the exercise sessions. And, we're trying to do something difficult. What do I mean by deterministic given the set of points? Exactly what it sounds like. I give you the set of points, you construct the graph. But you're not allowed to do any extra randomness. None of these tricks that the probabilists are always talking about. Right? Probabilists are always talking about, I'm going to run around and walk. I'm going to take some balls out of urns, or any of these silly things. None of that. You take the points as they're given, and you construct the graph. And yeah, what kind of answer could we hope for? What kind of behavior will this 1/2 average degree exhibit? So it will turn out, turns out that the average degree, at least for the Poisson, is always at least 2. Okay? This quantity, 1/2 the average degree, that's what we're calling the cost of this point process, or rather the infimum of this, right? The cheapest way to connect it up. So you don't need to worry about this normalization constant, just think about this average degree notion.
So when you say infimum, we're just taking deterministic ways of putting graphs on and picking the one that's most efficient, or rather, yeah, the infimum version of what
The infimum, yeah. Yeah, so I'll make a comment about this momentarily. Yeah, so the average degree, it's always at least 2. Okay, and whenever you're presented with some inequality, I never got much training in analysis, but you're supposed to ask things like, oh, how bad is the inequality? When is it sharp? And stuff like this. So it will turn out that you get equality. Remark, note, whatever. The average degree of one of these graphs for the Poisson point process specifically is equal to 2 if and only if G is amenable. OK? I think our friend SL3R is not amenable, so this is no good. This is a concrete problem. If you're seeing it for the first time, once you've gone through some of these exercises for the Poisson point process, I highly encourage you to think about it in some very concrete instances. And I'm going to issue these as challenges. Okay? So here are the challenges. There's 3 of them. The first one might seem a bit silly, but trust me, it's worth it. R squared. Okay? I gave you a hint. Amenability might be useful. But I mean, you should really sit down and concretely think about, like, what will these cheap graphs look like? It's a very concrete problem, but it's not so hard. So R squared, this guy will have cost 1. Okay? You'll be able to do average degree 2 plus epsilon for every epsilon. I mean, in this case, you can really get average degree 2 if you work hard. So that's one challenge. Let's go a little bit more hardcore. Let's think about SL2R. Okay. This guy turns out to have cost bigger than 1. Okay. So I can talk about that maybe in the breaks or something, but I would be very interested if this kind of audience could come up with an alternative proof of this fact. Because the proof that we have, I mean, it uses some more of this cost theory that Gaborio developed. It has something to do with being able to put a tree on this set of points.
So, sorry, when you talk about a group having a cost, you're talking about the Poisson?
Yeah, I'm talking about so it turns out that the Poisson point process has the worst cost, the highest cost. And so, yeah, strictly speaking, I mean for the Poisson. OK, that's another challenge. I encourage you to think about it. And here is the third one, SL3R. OK, this one's the main theorem of the paper, so that's maybe too hard. Let's do SL3R times Z. So this one, it will also turn out has cost 1. Why do I pick this kind of group? If you look at Damien's original Invenciones paper, where he develops the theory of cost, one of the first things he does is the discrete analog, the countable analog of this. Okay, they prove that a countable group times Z has fixed price 1. And people wanted to extend this to the non-discrete setting. Okay, so they knew that there was a way to define cost for actions of locally compact groups, PMP actions of locally compact groups, but people couldn't prove any theorems. And this is where I come in. In my PhD thesis, I proved some of the first non-trivial results about cost in the non-discrete setting. And maybe it sounds very modest, but I mean, this was genuinely a breakthrough. Okay, so the strategy that I employ for proving this is the exact same strategy that we do in the paper. Okay, so yeah, this is not just a challenge, but it's actually also on the exercise sheet as a guided exercise. Okay. Yeah.
Do we require the graphs to be connected?
Yep. Yeah. You can get away with less than this. You can get away with a unique infinite connected component, but this is something I'll talk about tomorrow. Okay. So that's the cost optimization problem. Those are some specific instances. I'd be very happy if you come up with some alternative answers for these problems. I mean, this one, if you can do R squared, I will be impressed, but I'm not going to be leaving mathematics. If you can do this one, I'll be quite impressed. I'm not going to leave mathematics, but I might flip through the job pages. Like, I think the lumberyard, or I don't know, the aquarium or something could be nice. This was my PhD thesis, so, well. Give it a go. I guess I use the
Would
rule.
you say that average degree equals 2 if and only if G is amenable?
Yep.
So for...
Non-compact, amenable.
Right. So if you're getting like fixed price one, if you're non-amenable, you mean like it happens by a limit or something like that?
So yeah, I mean, the consequence of this is that as soon as you're non-amenable, you can't really hope to attain this infimum, at least for cost 1. So you will have to construct a sequence of graphs. So that's the task. To prove fixed price 1, you have to construct these cheap graphs with average degree at most 2 plus epsilon for every epsilon. OK. So yeah, I've hyped it up. How do we actually attack cost? So how to attack cost? Cost, what I mean is the cost optimization problem. We do this via some technology that I developed in my PhD thesis. So this is joint work with Mikolaj Fraczyk. It's inspired by previous work of Arbeit Weiss and Kekris, but I'll talk more about this on probably Thursday. So I'm going to give you a kind of vague statement, but I'll tell you, what the takeaway is. So for cost optimization, the cost optimization problem, you can add extra randomness. As long as it's of the right type, OK? And I'll say a slightly vague statement, and then tell you concretely how we actually use it. You're allowed to add an independent sample of any what's known as weak factor of IID. Stochastic process. Okay, this is terminology that will make sense as the mini-course progresses. I will admit that this is a technical tool which is important in this paper with Mikolaj. Mikolaj refers to this as the mumbo-jumbo of the proof. Okay, but I do want to say something about it probably tomorrow. What am I going on about with this extra randomness? The extra randomness that we're going to add is this fantastic new object, the ideal Poisson Voronoi tessellation. Okay, so that's what I'll talk about now. So for this paper, we used the ideal Poisson Voronoi tessellation. It's a bit of a mouthful, so we abbreviate it IPVT. IPVT. Okay, so I'll tell you a little bit about this object. So what's going on with this object? You're all familiar with the Voronoi tessellation, I believe. Maybe you know it as like Dirichlet regions or something. But it's just some fundamental concept, some basic concept from metric geometry. Poisson here refers to the Poisson point process. Okay, so you take a sample of this Poisson point process on your group or on your symmetric space, whatever, and then you build this Voronoi tessellation. Okay, so it's a random tessellation of the space. And I want to let you know that this Poisson Voronoi tessellation is an extremely studied object. There are hundreds, maybe 1,000 papers on this thing. There's all sorts of applications, like applied math type ones. But it has received maybe less attention from the ergodic theory perspective. Yeah, and so I haven't really mentioned it yet, but this Poisson point process, it actually has a parameter associated to it, a numerical parameter. This is what I'll explain in the exercise sessions. It represents what's called the intensity of the process, the expected number of points that you see in a region, or the average number of points. And what we're doing here, what makes this an ideal Poisson Voronoi tessellation, is you're looking at some kind of limit of this Poisson Voronoi tessellation as this intensity parameter goes to 0. Okay? So this is the limit of PVT t. T is this numerical parameter as t goes to 0. Okay, it's an incredibly natural object to look at, and somehow it wasn't looked at until remarkably recently. So I should mention that this limiting tessellation, this is something that was studied in a PhD thesis of a student of Russ Lyons. We were not aware of this paper. What inspired us was a very beautiful paper of Budzinski, Kurian, and Petri. Oh. So this is a beautiful paper. They proved something about the asymptotics of Giga constants for hyperbolic surfaces. But I encourage you to look up this paper and take a gander at the images that are on the first 3 pages, the first single page. Yeah. So they made some reference to the existence of this kind of limiting tessellation. They had an extremely ironic name for it. It makes sense, but it's too ironic. They called it the pointless Poisson Voronoi tessellation. We use it for this cost and higher rank stuff, so maybe it's not so pointless. But what they mean is that somehow each cell has a point inside of it, and when you take the limit, the points disappear, right? So in this sense, it's pointless. But what's really happening, if you understand the geometry a little better, which they do in a subsequent work, is that the points are going to the boundary in some sense. They become ideal points. Okay? So now everyone calls it the IPVT. So this was the paper that inspired us. I also want to mention another paper where they study it for hyperbolic space. So this is Jagiellonian, Enriquez, Kurian, Enriquez, Lyons, and Unel. Here they study it in HD, but very much from a stochastic geometric perspective. Okay, but this is also a fantastic paper. I think it was recently published in Annals of Probability, and it has so many fantastic diagrams. Okay, they're very interested in visualizing this object, particularly these two fellas, Jagiellonian and Kurian. They gave me this little jewel thing. This is like one of the cells in H3. So if you're interested, you can have a look at that. Okay, so yeah, they study this in HD. They prove that this model exists. They prove various stochastic geometric statements. There's not really much overlap other than with our paper, other than the existence and the description of this object. Okay, so what is it that we actually prove? And just not sure how I do the attribution. There is some overlap with this paper, but that's a long sequence of names, so I'll just write it like this. Okay. So the limit object, the IPVT, exists. It really exists. And has an explicit description. explicit description as a factor, let's call it a factor, I'll explain this terminology tomorrow, as a factor of the Poisson point process on some homogeneous space. Okay, and here's where I create some controversy, but blame Mikolaj. G mod U. This U is maybe not the U that you're thinking of. Let me...
It's not the U that anyone in this room but you is thinking.
Wow. For now. Let me tell you what this thing is. So I have been asking the various experts who are familiar with these things what I should be calling this, what would be a better letter, what would be a better name. I don't know. But here, I mean, it's very concrete. U is the kernel of the modular function for a minimal parabolic. P inside of G is a minimal parabolic. Okay, so if you can come up with a better name for this subgroup, I would be very happy. Okay.
By factor, you mean weak factor?
No, I mean factor. I mean, it's like the IPVT itself is a factor of this, the Poisson on here, and then therefore it's a weak factor of the Poisson point process on G itself. Yeah, let me tell you the magical property of this subgroup. So you can probably tell that it's a closed subgroup, unimodular. And it has one other property that, well, two other properties that we need. So note, U is amenable. U is? You are. You are amenable. OK. U is amenable. And it satisfies another property that is maybe less obvious, but not difficult to check. It's what we call weakly normal. I think this might also be called S normality or Q normality. I struggle with this terminology. So what do I mean? What this means is that for har almost every G and G, this intersection of U with any of its conjugates, this turns out to be isomorphic to, well, some compact noise times r to the rank of G minus 1. OK? So in particular, so non-compact, the intersection is non-compact if and only if G has higher rank. OK, someone assures me that this is not very difficult to check in general. I can do it for SLNR and SL2R times SL2R. That's good enough for me. But maybe you're more advanced. OK, so now I have told you everything we need. Everything we need. This is all we need. To solve the cost optimization problem. Okay, all we need is this magical subgroup, which is weakly normal and amenable, and this mysterious theorem that I proved as part of my PhD.
So what is delta P occur?
You're looking at the modular function. So this minimal parabolic is not unimodular. So this is some non-trivial. You can write it down explicitly in coordinates if you want. OK. So we're running out of time, but fortunately I only have one page left. The other page is just self-promotion, so that's kind of untasteful anyway. So let me tell you what I really mean. I mean, I've mentioned these properties of amenability and this weak normality. How do they actually manifest in the IPVT? So this is the theorem that we prove. OK, so the first statement, this is not the juicy part, but it's logically necessitated. So the cells of the IPVT are quote-unquote hyperfinite. OK, so I was told that some of you know about hyperfiniteness, but a lot of you don't. This is connected to amenability. Okay, it's essentially the same thing as amenability of some associated equivalence relation. And I mean hyperfinite, well, I mean amenable in the sense of Zimmer. Okay.
In the sense of what?
Zimmer.
Oh.
Yep. So yeah, this is something that we need. I'll tell you what this concretely means for the cost optimization problem. But the juice is in the second statement. Okay, this is the goosebumps moment of the talk. I get chills whenever I think about this property because it's ridiculous. This is what we refer to as infinite walls. Okay, and so I'll give you an informal description first. In higher rank, almost surely every pair of cells, pair C1, C2 of cells of the IPVT yeah. So this IPVT, this is a random tessellation of your group or of the symmetric space below the line into infinite volume cells. These are the elements of the partition, if you wish. Okay, so they're infinite volume cells, and what I'm claiming is that in higher rank, almost surely every pair of cells of the IPVT touch. A lot. Right? Not just a little, but a lot. So in fact, this will be slightly more precise. In fact, for every pair of these cells, the epsilon neighborhood of the intersection of their common boundaries. So I look at the boundary of one of these cells, and I intersect that with the boundary of the other cell. I mean, this thing is not just non-empty, but this has infinite volume. OK? David reassures me that no one can draw pictures of higher rank symmetric spaces. I mean, it's a real challenge to try to draw a tessellation of a higher rank symmetric space with this property, right? Somehow all of these cells are snaking around, rubbing up against each other forever and ever. It's very strange, right? OK. So why do we care about these two properties? This is how I will most likely finish. I told you that if you're interested in solving this cost optimization problem, you're allowed to add extra randomness, as long as it's of the right type. And trust me, this guy is of the right type. Okay? And now I want to show you why this tessellation solves the cost optimization problem for you. So to compute cost, add an independent sample of the IPVT to the picture. I'm allowed to use this extra randomness to construct these graphs. Picture. Anush tells me that I say this word weird. I come from Australia. Picture. OK. And maybe I have enough room on this board. Oh. OK, so here is my best attempt at drawing a higher rank symmetric space. That's this potato. And now I've sampled from the Poisson point process It's also hard to draw because it's infinitely many points. This looks a bit too regular for the Poisson, but anything can happen in the Poisson, so this happens with some positive probability. And now I've sampled from this tessellation. The tessellation is a random tessellation of this space into these infinite volume cells, which I have no idea how to draw, so I just draw some kind of vague slices. Okay, there's infinitely many of these guys. And so by this hyperfiniteness property, this is something I might explain on Thursday. By one, we can put Z lines on the Poisson points in each cell. Okay, this goes back to work of Dye, Ornstein-Weiss, Kohn-Feldman-Weiss. This is some very known sort of thing. So the picture is something like, oh, well, I'm supposed to be drawing Z lines, that somehow there is a way of putting this kind of Z structure on all of the points, a connected Z. Okay? And I'm trying to solve cost optimization. I'm trying to minimize the number of edges. Trust me, this is the best guy to be looking for. He has average degree 2. Okay, this average degree notion, as you'll see, it's very intuitive. You know it when you see it. And I mean, this says constant degree 2, so surely it has average degree 2. Okay. But that means I've only got an epsilon left of room. This is where this magical infinite walls property comes in. So by 2, adding what I'll call stars extremely randomly, or extremely rarely and randomly. So by a star, what I mean is a graph that looks like this. What you do is you have some fixed point in the center, and then you connect to every other point in some epsilon ball. You may recognize this, this diagram from the poster for the summer school. Very thankful to whoever made that decision. So if I plug in these stars everywhere, well, the union is connected. The union makes us strong. The union is connected. Right? I'm free to move using these Z lines, these kind of train tracks, inside each cell arbitrarily. And infinite walls tells me that, well, I'm always going to find pairs of points, actually I'll find infinitely many, where the distance between them is less than epsilon, crossing between all of these cells. I find infinitely many of these. One would be enough. Infinitely many is good. Okay, the union is connected, and the average degree of this graph is at most 2 plus, I don't know, something small depending on epsilon. The average degree notion is intuitive, right? I mean, if I'm standing in the Poisson point process, and I look around in the epsilon ball around me, I mean, what are the odds that there's another point of the Poisson point process in that ball? That's got to be rare, right? Like exponentially rare, doubly exponentially rare. In any case, it definitely goes to 0 as epsilon goes to 0. So we get the good average degree. And
You really mean little O or big O there?
I guess big O, right? Plus small thing of epsilon. It's essentially the volume of the ball of radius epsilon. That's one of the exercises. So I'm looking forward to your solution. OK, so yeah, time-wise, things are a bit tight. So I'll just say some things. But I mean, remarkably, that's the end of the proof. OK? That's the whole story. This is the whole thing of the mini-course, is just convincing you of the details of this, whichever details you happen to be most interested in. And this statement that we have, I mean, it followed very quickly from this theorem A and theorem B. Theorem A, I've already explained to some of you very recently when I was in Paris at a summer school. I hope you liked that talk, because you're going to hear it again. But the connection between rank gradient and cost is actually remarkably clear. Okay? It's maybe like ineffective, but it's quite clear. And it's the same, basic fact from here, connecting like, yeah, what do I want to say? connecting fixed price in general to the cost of this Poisson point process. Yeah, so there's one picture associated to this theorem A. There is this picture associated to proving fixed price. And then the third picture, which is the most beautiful of all, it's not even close, is this infinite walls one. Okay, so this you'll probably hear about on Friday. It's a very, very nice proof by picture. It's like a magic incantation or something. You just draw the right diagram and you say the magic words, Mecca equation and Poincaré recurrence, and the whole proof is done. Okay, so I'm really looking forward to that. Yeah, when do I finish? Now, basically.
Oh, you've got 5 more minutes.
5 more minutes. Oh, wow. OK, perfect timing. OK, well, all I was going to do was just to say a little bit about the further literature in terms of this IPVT. So these are things I would be happy to talk about with people. But yeah, I won't write anything on the board because I've already used all the boards. This hyperfiniteness property, if hyperfiniteness is something you know that you're interested in, you might think that this is somehow automatic because this tessellation is a limit of, well, finitary tessellations. And what I want to inform you of is the fact that that intuition is false. I have a recent paper with Hector Hardon Sanchez, Antoine Poulain, and Conrad Rebel, where we show that there is no proof just using finiteness of the cells. Okay, so there is something going on there. I will talk about it briefly on Thursday. Another result that I want to advertise. So this I also won't speak about in the lectures really, but I should say it. This is an alternative proof of fixed price 1 in higher rank using something called Cox processes. Okay? So in the strict logical sense, this is much simpler than what we do with the IPVT. But I can be completely honest. I mean, I like these Cox processes. I have some questions associated to them. If you prove something about Cox processes, I'll be interested. But I'm just some guy. If you prove something about the IPVT, probably everyone will be interested in. So, in terms of directing your research efforts, that's probably more fruitful. Yeah, so this is, as I'm saying, like a strictly simpler version of this. If all you care about is fixed price 1 and the connection to rank gradient, this is the story that I would tell you if you were on your deathbed or whatever. OK, other things that we know about the IPVT. Russ Lyons, in this paper, asked if the cells are what's called indistinguishable. This is some property from probability theory, from percolation theory. And I proved that they are. It's some kind of ergodic property of this tessellation. This fella, Jagiellonian, I think he's down the street most of the time, at the university, not on the street. He proved this infinite walls property for H2 times H2, but with the L1 metric. Okay? And now it's really a shame that I don't have any space. The most exciting development, in my opinion, is a fairly recent paper of Jan Grebik and Konstantin Recker. So they proved some uniqueness property for Poisson Voronoi tessellation percolation in the low intensity regime, assuming property T and making use of this infinite walls property. Okay, so this is a very, very nice paper. In terms of the cost application, I guess it's slightly weaker, but you do end up with a more explicit cheap graph in terms of the cost optimization problem. OK, so I highly encourage you to look at that paper if you're interested in. Yeah, I think that's basically all. So I'll finish there. Yeah.
So you assumed this group G was simple?
Semi-simple.
But you talk about H2 plus H2.
Yeah.
So that's good. That's also semisimple.
Yeah.
Yeah. So it's different from.
L1 metric.
Yeah, different metric.
It works for standard metric as well.
It works. So we prove it for the L2 metric, and then he proved it for the L1 metric. The proof is like, I mean, this picture I was describing in terms of this Poincare recurrence thing, you could phrase it this way. But the L1 metric is kind of more interesting for guys like Jan Braddock for various reasons.
We also we construct the IPVT a bit differently, although it's probably equivalent. Like the Kelly paper and also the Jagiellonian paper does explicit convergence of tessellations.
Yeah. But in terms of cost, you can get away with some abstract MongoDB. Yep.
Which of those properties are known to fail for each?
I mean, it's the infinite walls comes from this computation at the top. So, yeah.
And the hyperfiniteness?
Hyperfiniteness, this is true in general. As long as your group is exact, it's you're good to go.
More questions? Just going to add my own challenge, which is if you can draw me a picture that convinces me of what this infinite wall tessellation looks like in H2 cross H2, I don't know, I'll buy you lunch.
Can you draw the picture of H2 cross H2 first, and then I can put a tessellation in there?
Fair enough. I can draw H2 and I can draw H2. Yeah. All right, let's thank Sam again.